So example 1, okay, we're looking at a semicircular current. Okay, semicircular current loop. We want to, as an exercise, we want to figure out what is the magnetic force on the semicircular part of this of this current loop. Assume the current flows counterclockwise. Okay, so the current flows like this. Now, it is exposed to a uniform magnetic field pointing in the same plane, within the same plane which contains the semicircular loop. The semicircular loop carries a current I and has a radius of r, okay, a fixed radius of r. Now, let us find the net force on the arc, on the semicircular arc. To do so, let us find the first of all dF on this little segment from here to there. Okay, this little segment, I have I ds. ds points from here to there, right, along the direction of current flow, cross B, right? Cross B. Okay, and then I can integrate between here and there along the arc. We call this contour C, from here to there. Okay, it's only a semicircular arc, doesn't include that straight part. So that would be the magnetic force on the arc. Okay, will be the magnetic force on the arc. The question now is how we calculate it. Well, what you can do, you follow the textbook. What they do is, first of all, they follow the definition of ds cross b. That would be ds. I can can be taken out. ds times b times sine of the angle between them. Okay, what is the angle between them? This is ds and b is right there. So that is b. It is this angle we're talking about. Okay, what is this angle equal to? If that angle is equal to theta, okay, see this line is perpendicular to this line, and that line perpendicular to that line. Doesn't that tell you this same angle theta? Okay, it's the same angle theta. So really, it's just sine theta. So what you can do now is take the b out, which is a constant, okay, and then rewrite ds in terms of the angle theta. ds, as you know, is just r being the radius, r d theta. So you can write this as I times ds times b times ds, which is r d theta. I'm taking r out, sine theta d theta, right? Going from here to there, so theta go from 0 to pi. What's the integral of that? Well, it's easy to work out this integral, and it's just negative cosine theta, and going from 0 to pi, you find the answer to be 2. Okay, so this really is just 2I b r. That is a recount of how the textbook treats this problem, which of course is correct. However, there is an easier way to do it. Okay, it's not in the textbook, but there is definitely an easier way to do it. You realize that the magnetic force, the magnetic field B, as a whole vector, not just its magnitude, the whole vector is constant. Okay, it never changes from place to place. So I can take that out of the integration along with I. So another treatment would be this. Would be F equals what? Taking I out, taking B out. I'm going to only retain ds in integration. Now, careful. About the semicircular loop, you're adding all the ds's up, okay? One after another, after another. What are you getting? You will be getting a vector pointing from the beginning of the loop to the end of the loop, right? That's how we sum over all the ds. What is that? That's a vector with a length of 2r, right? Diameter, pointing this way. Now, if it points this way, when it crosses B, you get a magnetic force, right? You get a magnetic force. The direction of the force is inward, okay, into the blackboard, into the paper, because it's this vector cross B, actually. This vector goes like this, cross B, so this vector cross B. You get a force into the paper. And what about the magnitude? The magnitude is determined by this magnitude, which is what? Which is 2r, right? Times that magnitude times the angle between this vector and that vector. That's 90 degrees. So, as far as the force is concerned, okay, actually, be careful here. I should be more careful. I should write here just the force itself, the magnitude itself, because that's just the magnitude. So as far as the magnitude of force is concerned, we know the direction is pointing inward. The magnitude will be I times 2r times b times sine 90 degrees, right? Isn't that the same as that? 2ir b the same as that. We don't even have to finish this integral. Okay, just just integral, figure out the result of this integral over ds, so you can get the same result. But even that is not the simplest answer. There is an even easier way to do it, because didn't we realize in just the past page, right, that the net force on a self-enclosed current loop is always equal to 0 as long as the B field is uniform? We have a uniform B field. We have a semicircular self-enclosed loop. So isn't it true that the net force on this entire loop should be 0? That means the force exerted on the semicircular part plus the force exerted on the straight part must be 0, right? Okay, that means the magnitude of the force on the semicircular part should be equal to the magnitude of the magnetic force on the straight part, and the direction will be just opposite. Okay, now on the straight part, it is much easier to calculate, right? What is the magnitude of the force on the straight part? What is the magnitude of the force on the straight part? You can do I ds cross. In fact, you don't have to do that. It's just I L cross B, because it's a straight segment, so you don't have to integrate anymore. What's L? L goes from here to there. Okay, so I L cross B. L and B are perpendicular to each other, so the magnitude would simply be what? Would be I times the magnitude of L, which is 2R, times the magnitude of B. That's it. That should be the magnitude of the force on the semicircular loop, because that should have the same magnitude as the force on a straight segment. Okay, so you see, you recover the same magnitude. You can even recover the same direction, the correct direction, because the force on the straight segment, okay, L goes this way, B goes that way, so if you use the right hand rule, it sticks out of the paper. That is the force on the straight segment, and the force on the semicircular part should have the opposite direction, going inward. Okay, so that in fact is the correct direction. So however you do it, this is an example how to calculate the magnetic force on a curved current. Okay, next let's consider a simpler geometry. A current loop made of a rectangle shape into a rectangular shape. We know if we expose this current loop to a uniform B field, then the net force on this loop will be 0. We know that. Okay, but does that mean the magnetic field doesn't do anything to it? Well, it can still exert a torque on it. In fact, we can see from this example, and this is not just an exercise to calculate the torque. This setup has very important practical applications. It is at the heart of the generator, which produces electric energy, okay, based on other forms of energy. That's how a power generator works. Okay, so let's see how it goes. Suppose I have a rectangular loop. Okay, I drew a solid line indicating that this side of the loop is closer to us and that side is further away from us, and assuming there's a current flowing in this sense. Okay, you put it in a magnetic field B pointing this way, and I'm going to define a direction, a positive direction, which is perpendicular to the plane containing the loop, and it is also such that the direction satisfies the so-called right-hand rule, and that is I'm going to use my right hand, these 4 fingers, to wrap around the direction of the current flow. So in this case, it's clockwise, it's counterclockwise like that, and the thumb would tell me the direction of that vector. Okay, otherwise I couldn't tell whether it's going this way or that way. It is perpendicular to the loop, but it also satisfies the right-hand rule according to the current. Okay, so here is a vector. It's got a magnitude that is equal to the area of the loop, and the direction is determined by the right-hand rule according to the current flow. So the current flows backwards, that vector will point downwards. Okay, so the angle between A and B is theta. Now, I want to calculate the net force and the net torque on this 4-segmented rectangular loop. We know the net force equals 0, we just want to verify that. But what about the net torque? That is the more interesting part of it. To do so, let us take a side view. Okay, side view. That is, I'm going to look at it from here. Okay, I'm going to look at it from this angle, going this way. So what I see here is the only thing I can see with a whole view is this side. Okay, so it's this side. The other side is obstructed. And then here is this part is really this part, and that part is really that part. So here, when you look at it this way, you see a current flowing towards you, right? That's a symbol of a vector going out of the paper. And here you get a vector pointing inwards, because you look at it from here, you see the current flowing away from it into the paper. So this is a side view, okay? And the current in this segment points like that, right? Points like that. And using the right-hand rule, okay? Using the right-hand rule, wrap around the direction of the current, and then you have a correct direction for the vector A, perpendicular to the loop. And the B field is like that. Angle between them again is theta. Here is 90 degrees. Okay. Let us find the net force first. You have to find the force on all 4 segments, and we add the forces together. First of all, the force on this segment, okay, on this segment, what is that equal to? Well, it's I L cross B, okay, I L cross B. L is from here to there, L cross B. So L cross B, you get a force pointing out of the paper, right? L is like that, B is like that. So L cross B, don't you get a force pointing out of the paper? But what about the force on that segment? The force on that segment is also IL cross B. The only difference is that L is not reversed. L is like that, okay? So you will get a force pointing into the paper, right? So the force, obviously the force exerted on this segment cancels with the force exerted on that segment, okay? Similarly, we can see that the force exerted on this guy and that guy also cancel out in terms of magnitude and direction. Let's see, the force exerted on this guy. You got a current flowing out of the paper, okay, out of the paper, and then you have B. So it's L cross B. L is outward like that, B is like that. So what do you get? What do you get? L cross B, L cross B. You get a force like that, right? Okay. Now, similarly, what is the force? What is the direction of the force exerted on that current? That one, okay? L points into the paper, so L cross B, L cross B, you get a force like that. See? Okay, so these two forces, they have the same magnitude. You can see that clearly. And they point in the opposite direction as well. So what is the net force again on this loop? 0, as expected, okay? With any shaped loop, as long as the B field is uniform. But there is something about this pair of forces. Even though they have the same magnitude and point in opposite directions, they're not along the same line. See that? Unlike the force on this guy and that guy, these two forces, one on top, one on bottom of segment of the loop, they are not collinear, which means they cannot cause any net force, but they can cause the loop to turn. They will exert a torque. Okay, that is what we're interested. Now, what we want to know is, if you're using point O as a reference point, what is the torque exerted on the loop due to these two forces? Okay, let's see here. First of all, what is the magnitude of this force? Well, it's L cross B, L out of the paper, B going that way, so L and B are perpendicular to each other, right? And if the length from here to there, we call it A, okay? And then I know what that is. That will be just I, L, which is A, times B, times sine 90 degrees, okay? So that is the force IAB. Similarly, you also have IAB here. Okay, now let us look at the torque exerted by these two forces at point O. You know how to calculate torque, don't you? Still remember that? Here, okay. This is the line of action of the force. Okay, the way we define torque is the product of the force magnitude itself times the so-called lever arm. What is the lever arm? The lever arm is the distance between the point of interest, which in this case point O, and the line of action. So that is the lever arm. Okay, that is the lever arm, 90 degrees. How do we find the lever arm? Well, this angle is theta, right? This angle is theta. And if this length we know, then we can find the lever arm, right? We can find the lever arm. How long is this length from here to there? Remember, this point is the middle of the loop. It's at the middle of the loop. So the distance between here and there really is half of that length. If I call that length B from here to there, then this from here to there is half of B, right? So half of B, and then how long is this lever arm? That will be half of B times what? Sine theta, right? Sine theta. So half of B times sine theta. Okay, that will give you the torque provided by this force. Okay, now what about the torque provided by that guy? First of all, these two torques are in the same sense, which means in this case both are clockwise. Okay, so they add together, do not cancel each other out. And secondly, they have the same magnitude. Okay, they have the same magnitude because the force has the same magnitude and the lever arm also has the same magnitude. So the net torque is just double that amount. Torque, the magnetic torque, has this magnitude. Okay, cross out the two, this 2 and that 2, and what we get is I times AB times the magnetic field times sine theta. What is A times B anyway? Distance A, distance B. So that will be just the area of the loop, right? It's just I A B sine theta. Okay? Now, this is an important result to know. There exists a magnetic torque on this current carrying loop. The torque wouldn't be 0 unless sine theta is 0. And that can only happen if the loop points, in other words, this vector A points either along B or anti-parallel to B. In other words, that only happens, okay, that only happens when the loop is oriented perpendicularly to the magnetic field. Okay, perpendicular to the magnetic field. So the B field exists in such a way that it tends to turn this loop so that the loop eventually is perpendicular to the B field. That is the only point where the torque will be 0. Okay, so it will turn the loop if the loop carries a current, and that is an important observation that we'll see, that will make great use later. Now, this is the magnitude of the torque. What about the direction? We know the direction in this case, the torque is, or the sense of the torque, right? It's clockwise. I can recover that direction by using simply A cross B, right? A cross B also turns in. It's just clockwise. And what about the magnitude of the vector A cross vector B? Isn't that A times B times sine theta, which is exactly what I have, right? So I can rewrite torque as the vector torque as tau equals I A cross B. Okay, that is more elegant than that expression. It contains both magnitude and direction. And we have this combo here: the product of the current times this vector A, which has the magnitude as the area of the loop and is perpendicular to the loop. This combo, I times A, we give it a name. We call it a magnetic moment, mu. Okay, so here is how we define the magnetic moment. Suppose I have a loop carrying a current. It doesn't have to be a rectangular. Any loop will do. Okay, carrying a current like this. One can define a magnetic moment for this loop first of all, using the right-hand rule, wrapping around the direction of the current. You introduce a direction of mu. Okay, it's the same as direction of A. And what is the magnitude of the magnetic moment? It is equal to the product of the current and the area A, which is contained by this loop. Okay, so that's mu. That's mu. Again, mu is defined as I times A. Magnetic moment. Once you have this magnetic moment, you can write torque as mu cross B. Okay, mu cross B. The you put a loop of magnetic moment mu in a magnetic field B. Here's the torque you're going to get. Okay.